So we've discussed that we want to use normalization on this quaternion. We want to renormalize the quaternion instead of using some of these other traditional methods for taking care of orthogonality error. Okay, so we've motivated that previously, and I just like to take a moment and talk about methods for normalizing the quaternion. So we have this basic equation here. So this is the equation for a normalized quaternion is equal to the current quaternion divided by the length of that quaternion, okay? And the orthogonality error we've defined previously as 1 minus the length of the quaternion there, okay? So so we can actually plug this in, and so I'm just going to plug this into there and rewrite this as e over the square root of 1 minus epsilon. Okay, that's another way to express the, or another way to renormalize this quaternion. If I first computed the error, then I could plug it into this equation here, and that's it. You know, that would renormalize my quaternion. So it turns out that this method requires several things. So in order to do this, we have to square several terms, and then we have to take the square root, and we have to perform a division. And all of that can be kind of computationally expensive if we're going to run this every single time step. So we're just going to look at one way we can speed this up and get something that's approximate and still plenty accurate, but is much faster. Okay, and this method that I'm going to talk about, it can be quite a bit faster. Actually, it can. I'd have to look at the numbers again, but I believe this method here can be 50% to I think 250% as long as the method that I'm going to present now. So. Okay, so what we do is we take the Taylor series expansion of this, okay, because epsilon is small. So anytime we have a function where the independent variable is going to be small, we can get a really nice approximation for that function by using a Taylor series expansion, okay? So let's walk through that. So we've got a Taylor series expansion of this equation, and remember, the Taylor series basically says that I can approximate f of, let's say, f of y, or f of x. That's probably a better variable to use here. Let me just swap that out. So f of x is equal to, or approximated by the function at 0 plus the derivative of that function evaluated at 0 times x divided by 1 factorial plus the second derivative evaluated at 0 times x squared divided by 2 factorial. Okay, and we could continue on adding higher orders here, but we're just going to take these first terms here, and we're going to approximate this function, this function here, and with this Taylor series expansion. Okay, so what we need here is we need f of 0. So f of 0, we just plug in a 0 for that epsilon. Remember, epsilon is our independent variable here. So if we plug in a 0 there, then f of 0 is just going to be 1 minus 0 and then the square root of 1. So that's going to give us just the quaternion. Okay. Now we need f prime of 0, and f prime, so we need to take the first derivative of this, and in order to do that, I'm going to rewrite this as e, the quaternion, times 1 minus epsilon to the minus 1/2, okay? So let's take the derivative of that, so that's going to be, let's see, the derivative of that is going to be minus 1/2 times e times 1 minus epsilon to the minus 3/2. Okay, so all I've done is taken the derivative. This is my function, and I've taken the derivative with respect to epsilon, and so that's what I get here. Now let's just make sure I did that correctly. So I took the minus 1/2 down front, Put it right there, e times 1 minus epsilon to the minus 3 halves. I have to subtract off 1 up there. Okay, so now we're going to evaluate this for when epsilon is 0. And so let's just plug in 0 there, and what we're going to get is minus 1/2 times e. Okay. Okay, so let's plug both of these now into this equation here. So our function, our quaternion renormalized. Remember, this is the function that we're trying to approximate. So the approximation for that is going to be equal to f0, which is just e. So we plug in e. And then plus f prime at 0 times x, which is epsilon for our case. So let's plug in f prime. So that's the minus 1/2 of the quaternion e. And then we've got to multiply it by x, which is, in our case, we're using epsilon, right? So we're going to plug in epsilon there. And then divided by 1 factorial, which is just 1. Okay, so we can rewrite this as e times 1 minus 1/2 of epsilon. Okay, now let's see, did I do that correctly? Okay, so I actually made a mistake here. When I took the derivative, I did the derivative of the outside, brought down that minus 1/2 out front, and then e, and then I needed to multiply by the derivative of the inside, which is a minus 1 there, epsilon. So that actually makes that a positive, and that's a positive there. And so this will be a positive, and that will be a positive. Okay, so there we go. This is another way to renormalize that quaternion. And this is actually significantly faster. Like I said, this the traditional method can take anywhere between 50% and 250% longer. It depends on how long a square root or divide takes on your processor, on the actual hardware that you're running on. So this can be significantly faster. It is not exactly quite as accurate. We're using this Taylor series expansion. We're only including the first 2 terms, and so we're neglecting higher order terms here. But because epsilon is so small, especially if we're applying this every single time step, it turns out that this is really quite accurate. So this is a really nice way to handle renormalizing of the quaternion. Every time step, if you apply this, if you keep the errors small, then you can use this equation here to renormalize that quaternion.